On this video, we're going to analyze the graphs of logarithm functions. So let's get started. So the first thing that we want to do is we want to graph the function log of x. And let's identify some of the properties. Now the first thing to realize is that there is no base for this log. So what we're going to do here is that every time we see log of x, we want to use the standard base, where the standard base is 10. So really, when we write down log of x, we're always going to assume that the base is 10. So if there is no base written underneath the log, we're always going to assume that it's base 10. Now, what we want to do is we want to graph this function and we want to identify these properties here. So let's get started. So if we graph log of x, we have the following graph here. Now, the first thing that we want to identify is the domain of this function. Therefore, we just want to take a look at the values of x's that this function takes. So let's see. Now notice that there is no negative x value that this function is using, because even if we zoom out here, notice that it never crosses the y-axis. So we know that it's only going to be using positive values, or those x values are greater than 0. So now the question is, does this graph ever use the x value of 0? Well, let's analyze this and let's do some algebra. Now, let's assume that the function, it includes 0. Let's assume that it includes the value x equals 0. Then we have y equals log of it, or log of 10 to 0. Now, what we want to do is we want to see, well, if I evaluate the log of 10 to the value of 0, what is the outcome? Well, it might not be that easy to see, but let's try to rewrite this. Let's try to rewrite this using our exponential expressions. So we know that we can just take a look at the base of the log, which in this case is 10. Raise it to the what is equal to, which in this case is a y, and now that is going to be equivalent of what we want to evaluate, which in this case is 0. So now our job is the following. Is there ever going to be a y value that makes this a true statement? So 10 to the what gives you 0. But notice that there is no y value. There is no y value that will make this a true statement. So therefore, we cannot include 0. So we already shown that we cannot use 0, but notice that this graph only uses positive x values. So therefore, my domain, using the interval notation, it is from 0 to positive infinity. Now, how about the range? The range talks about the y values. Well, notice that on the left-hand side, if we continue moving this function, moving to the left-hand side, notice that my y values are always going to be decreasing. And if we move this function to the right-hand side, notice that my y values, they are increasing, but very slowly, but they are increasing. So therefore, it goes from negative infinity all the way to positive infinity. So therefore, my range, it is from negative infinity to positive infinity. Now, let's take a look at the intercepts. One thing that we can conclude is that my function, it's never going to be touching the y-intercept, because we already shown that we cannot include the value x equals 0. So therefore, we can only assume that the only intercept is right here at 1 comma 0. So let's just write this down. So there is one intercept, or in this case, there is an x-intercept at the value 1 comma 0. But why is it that the x-intercept happens at that value? Well, remember that what we want to graph is y equals log base 10 of x. And if we rewrite this function using our exponentials, we're going to get 10 base y, and that is going to be equivalent to x. Well, let's pick one point. Let's pick the point of 1 for x. So let's plug that in. So 10 to the y equals 1. And now we think, well, what y value will make this a true statement? So 10 to the what can give me 1? Well, there's only one value that we can use for that, and that is 0. So therefore, we got 10 to the 0 equals 1, which is just 1 equals 1. So that is true. So therefore, 1 comma 0, it is a value that is on my function. It's a true statement. Now, where is my function increasing? Well, in order to identify the interval where it's increasing, we want to see is my function ever going to be lowering in y values? Well, notice that we go from left to right. If we are at this point in our graph and we keep moving to the right hand side, notice that we're always going to be increasing in y values. We're always going to be increasing in y values very slowly, but notice at 1.27, if I move a little bit to the right hand side, we get 1.31, which is the y value is bigger. And if I move a little bit more to the right, I get 1.37. So notice that the y values are increasing very slowly, but they're definitely increasing. So notice that this function is increasing at every single value where the function has been defined, but notice that the function is defined from 0 all the way to positive infinity. So therefore, it is increasing from 0 to positive infinity. Now, do we have a vertical asymptote? Well, looking at this function, we can kind of see that there's a vertical asymptote at the value x equals 0, because we already shown that we cannot use 0. But notice that if we keep scrolling, oh, well, I don't know why it's showing undefined, but we should have just stay super close to 0, super close, but not exactly on 0. So therefore, there's a vertical asymptote at x equals 0. So anytime we write down the function log of x, this will always be true. And notice that this is just the standard form of log of x. Sometimes we can just add a value inside the parentheses, or we can change the base. But if your function is being defined as just log of base 10 of x, which is the standard form of a logarithm function, these are going to be true. The domain is from 0 to positive infinity. The range is from negative to positive infinity. We only have one intercept at 1 comma 0. It is going to be increasing everywhere the function has been defined from 0 to positive infinity, and we have a vertical asymptote at 0. So now this is one type of logarithm functions. Now, there is a second type of logarithm function, and for that we're going to use ln, where ln is what we call the natural logarithm. Now, the first thing to realize is what exactly is ln? Well, recall that ln, it's a log function with a very specific base, and that base is the Euler number. So this is the difference between natural logarithms and regular logarithms. And the difference is that for natural logarithms, we're going to use ln, and the difference is that the base will always be the Euler number. Now, sometimes you might see some examples where perhaps we write down f of x equals ln of 7 of x. But this can also be represented as a logarithm function. So most of the time, we're just going to use ln whenever we refer to as having a base of e, or a Euler number. So how is this function different compared to log of x? Well, let's see. Let's graph it and let's compare. So here we have our natural logarithm function. So let's analyze it the same way that we analyze the log function. So what is the domain of my natural logarithm? Well, notice that it seems to be having the same information, which is we seem to be having an vertical asymptote at x equals 0, and we're only going to be using positive x values. So therefore, my domain is from 0 to positive infinity. Now, how about the range? Well, the range refers to the y values, and notice that it's behaving the same way. It goes from negative infinity, and if I keep moving to the right-hand side, it is going to positive infinity. So therefore, my range, it is also from negative infinity to positive infinity. Now, do we have any intercepts? Well, I can see one intercept right here. But note that that is the same intercept, 1 comma 0. Is it increasing or decreasing? Well, we can see that it's increasing the same way that it was increasing with logarithm functions. And where is it increasing? Well, it is increasing where it is defined, which is from 0 to positive infinity. Does it have a vertical asymptote? Well, notice that, yes, it does have a vertical asymptote at x equals 0. And it seems like I typed this twice, so that's fine. So now, if we compare the values, notice that they kind of have the same domain. The domain is from 0 to positive infinity, domain from 0 to positive infinity. Range from negative infinity to positive infinity, same range. Same intercept. It is increasing function from 0 to positive infinity, and it has the same vertical asymptote. So what's the difference? They seem to be having the same. Well, if we graph one function on top of the other, you will see that the natural logarithm function, it increases at a faster rate. And that seems to be the only difference between them two when we write down both functions in standard form. So they do have the same properties, same domain, same range, same intercept. It is increasing and it has a vertical asymptote at 0, x equals 0. And the only difference between them two is that the natural logarithm is going to be increasing at a faster rate. And with this, it concludes our lesson for the analysis of the graphs of logarithm functions.